Hello and welcome. This is Danielle Dumont at the Freshwater Trust, and we thank you for joining us for this webinar where we're going to explore the concept of quantified conservation and translating restoration actions into quantified conservation outcomes. Before we dive in, I'd like to just give a few housekeeping notes. We'd like for you to ask questions, so at any time throughout the presentation, you can type your question into the questions box that you will see on the right side of your screen. We'll be able to address some of those questions throughout the presentation, as well as we'll leave time at the end to answer more. Lastly, we also are recording this webinar, and so it'll be made available for later viewing. Now I'd like to introduce our presenter for today. She's Julia Bond, Science Director. Julia leads the science and research efforts at the Freshwater Trust. Here she directs the application of new models to the analysis of freshwater ecosystems. What that means is that she provides key analytical support for water quality trading programs, conservation actions, and policy work, all related to quantifying environmental benefit, or as we call it, environmental uplift. Over the past 4 years, Julia's work has allowed her to dive pretty deep into environmental data and models. So now I'd like to turn it over to Julia for a quick introduction of the Freshwater Trust and then our discussion of environmental uplift.
Thank you, Danielle, and thank you everyone for joining us today. I'm excited to take this opportunity to talk to you about the work that we've been doing, talk to you about a lot of the tools and the methods, and give you a few examples of projects on the ground and the results associated with those projects. So the Freshwater Trust, we're a nonprofit organization. We're headquartered here in Portland, Oregon, and we've been working for many years now to preserve and restore freshwater ecosystems. And to do so, we have a number of different programs here at the Freshwater Trust. We have a habitat restoration program where we're working to improve in-stream conditions for aquatic organisms, particularly focused on fish, to try and improve habitat and the functional conditions for aquatic organisms. We also work to restore in-stream flow, so that's working with landowners to agree to leave their water in the stream for the purposes of beneficial use instead of applying that on the landscape for agriculture or irrigation. And then more recently, we've been working in the space of water quality trading. So we're looking to identify restoration projects that can be used to address compliance obligations. So looking at permit holders, NPDES permit holders, or other dischargers who have a restriction to their discharge to surface water bodies. So that's just a quick background of some of the work that we've been doing. And I really wanted to take today as an opportunity to talk you through the specifics of some of our projects on the ground and the framework that we use to evaluate and assess the types of projects that we're putting on the ground. So that's this idea, as Danielle just mentioned, quantified conservation. And it's a shift that we've taken over the past few years to change the focus of our work from just counting the actions that we're putting on the ground, so say how many trees we're planting, to quantifying the outcomes of those actions. So what is the increase in shade that you're seeing from planting streamside trees? What is the improvement in water quality associated with those types of restoration actions? And the reason we care, the reason why we've made this change, this shift in focus, is we want to be able to track our progress. We want to understand what we're doing, how that actually works towards improving water quality conditions, how that really changes and improves in-stream conditions to improve and meet those habitat goals. We're also using this method to prioritize our actions so that we're putting the best actions in the right places to get the most environmental benefit. And what we've seen over the years is that we've really been very good as an environmental community at quantifying and identifying the environmental impacts that are out there, so what's wrong with the watershed. But we haven't been nearly as good as trying to track our progress towards meeting and changing those conditions on the landscape. So what we're doing with quantified conservation is changing that approach, and we rely on a number of different things. We rely on models, measurement, we rely on monitoring in order to understand these practices and what we're doing. So we use models. They're a representation of environmental systems. It's usually a mathematical simulation of the biological, chemical, or physical characteristics of a landscape so that we can predict change as a result of a restoration action. We want to be able to understand what the benefit will really be when we put that project on the ground. So this has all been a change that we've been trying to implement here at the Freshwater Trust over the past few years, and we started this back in 2012 with our Uplift Report, and we've been doing it ever since. And the goal of the Uplift Report is to understand the impact of our work. What are we really doing on the ground, and how is that actually improving conditions on the landscape? Instead of just tracking the actions that we're doing, how many trees we're planting, we want to understand the benefit to the river as well. And so we're doing that with our Uplift Report, which is what I'm going to spend a little bit of time today telling you about our most recent version, which is 2015. We're tracking all of the projects that we implemented in 2015, and I'm going to give you a couple of examples and introduce you to some of the results that we have for our projects this year. So instead of talking in generalities and trying to talk over with a big broad overview, I wanted to dive into a specific example, so a case study that we have of one of our 2015 projects. So this is the Cedar Creek project site that I'm going to start with, and Cedar Creek is a tributary of the Mackenzie River within the Willamette Basin here in Oregon. It's an important water body within the Mackenzie. It's a salmon stream, and what we see with so many of our rivers here in Oregon is we have a lack of streamside vegetation. We don't have riparian cover. Many of our stream sides are dominated by invasive species. We have a lot of invasive Himalayan blackberry here, reed canary grass, that really take over and create some of these monocultures of plants, and they don't really provide the same level of benefits that a native riparian forest would. You don't have the same level of shade or filtering capacity for these different streamside areas. So the goal of the Cedar Creek site was to improve riparian conditions. We wanted to increase shade and improve thermal conditions within the creek itself by shading the river. And what we have realized over the years with these projects is while that may have been the initial goal, there are additional ancillary benefits associated with a riparian buffer. This buffer is adjacent to an agricultural field, so it filters runoff, so it reduces nitrogen, phosphorus, and sediment loads to the river as well, all through the planting of a native riparian buffer strip. So what I'm going to do now is step you through some of the characteristics of Cedar Creek itself, the models that we use, the different approach that we use to look at these different characteristics, and how we really took it from a project that we put on the ground to the benefits that we're quantifying in our Uplift report. So here's our Cedar Creek site. These are the pre-project conditions. You've got an aerial photo here, and you can see that the creek is in the middle of the screen, flowing from the right side to the left side of the screen. And you can see the agricultural field just to the south of the creek. And what you probably notice here is while there is green next to it, there aren't many trees that are present on the landscape. It is very, very short vegetation, not a lot of trees, not a lot of buffer from that adjacent land use. And what you'll see on the south is we do have an actively managed field. We have active agriculture happening adjacent to this project site on that southern portion. So just switching the view a little bit for you, it's the same spot, exact same location, but instead of showing you the aerial photography underneath, we've got the topography. So we have the landscape. You can see the hill slope that's present on the site. And what you see with those green areas, that's the current riparian condition. That's the current vegetation, the current trees that are present. And you'll notice that you don't really see a lot on that southern portion of that stream bank. There really isn't a lot of vegetation that's present there. So what we were looking to do here is planting a riparian buffer, native trees and shrubs that come with a nice mixture of different species to try and improve biodiversity and all of the other habitat benefits that come from a riparian forest. So this was all planted in 2015, but what we want to do is not only implement that site, but what we wanted to do is understand those environmental benefits that are associated with that project site. So I'm going to step you through a little bit of the modeling that we did to quantify those additional benefits associated with that riparian revegetation site. So here's the planting area of Cedar Creek, the yellow area that you see on the screen. All of that was cleared of invasive species. We went in and treated all of that, removed all of the blackberries, removed the reed, treated for the reed canary grass, and planted that with that native tree and shrub mixture. Lots of different tree species, different types, some black cottonwoods, some cedars, assortment of different tree species planted here. And the yellow area encompasses the entire planting polygons that were delineated by the project manager and then planted back in 2015. So the model that we use to quantify the environmental benefits that the uplift, if you will, from the project site is the shadolator model, which is a module of the heat source model. And what this model does is it quantifies the incoming solar radiation that reaches the surface of the stream under different conditions. And it incorporates a whole bunch of different components, different parameters that are used to make that and complete that quantification. You have the surrounding topography, so if you have cliffs or hills nearby that shade the surface of the stream, those are incorporated. You include the stream aspect, so what direction does the stream face? Is it north, south, east, west? All of those impact the shadows that can be cast on the surface of that water. You also have the stream width, so how wide is that stream? How much surface area exists. And we run two scenarios. The first one looks at the current conditions, and that is the current incoming solar load that is based on current site conditions. So that is the current vegetation that's present. So whatever shade or shadows are produced by the vegetation and the topography currently present at that site. And you have an incoming solar load. In the case of Cedar Creek, it's a pretty small amount of shade that we currently have given the lack of vegetation. We then model a future condition. So all of the same parameters, all of the information in terms of topography, aspect, width, all of those things remain the same. The only difference in our future condition scenario is the height of the vegetation. And this is a simulation. We're looking at what mature trees will look like. What are the characteristics of a mature black cottonwood? How tall does it get? How big does the canopy get? And that's what we're using to model that future condition, and we quantify the incoming solar load that reaches the surface of the stream under that future condition. The difference between that current condition and the future condition represents the thermal benefit from that riparian planting, and we express that using an energy load. So we're looking at the units of kilocalories per day in this particular case. And the difference between those is the uplift that we're seeing from the Cedar Creek riparian buffer in terms of kilocalories per day of solar load that was blocked from reaching the surface of the stream. And we care about solar radiation because it's one of the drivers of water temperature. Incoming solar radiation can warm streams, and it can degrade the thermal conditions, which are so important for fish, particularly in the Pacific Northwest where we have salmon, steelhead that really require those colder water temperatures in order to thrive. So back to the planting area, so you understand hopefully the modeling parameters that we use. So we're looking at that pre-project condition, what the current shade looks like based on the current canopy, and then modeling a future condition, what that reduction in solar loading will be based on planting this yellow area that you see on the screen. And so, as I mentioned before, we're looking at a future condition. We're looking at what that canopy will look like once those trees mature. And so you can see now, instead of having that really bare topography, that really bare area, instead you have a much higher canopy, a much fuller riparian canopy that is able to shade the surface of the stream and keep the water cool. So when we're looking at this as actual benefits and what we're trying to track over time, as I mentioned before, we're expressing that as an energy load. That's a kilocalories per day. We have the load coming in pre-project, so that's 38 million kilocalories per day, and seeing a reduction of just about 13 million kilocalories per day. So that is solar loading that is no longer reaching the surface of the stream once that canopy continues to mature. So the thermal loading is one of the pieces, and really I would say that when we were thinking about this project and originally designing it, the goal was improving riparian conditions, particularly with a focus on reducing incoming solar loads and improving shade. However, there's a lot of additional benefits associated with a riparian zone, especially a healthy forested riparian area. And that is those additional white boxes that you see on the screen now, the phosphorus, nitrogen, and sediment benefits that are associated with a riparian buffer. And what we have here are those additional ancillary benefits that were perhaps not really part of the original goal and design of the project, but that we are able to track as well and model those additional benefits over time to see what the ancillary benefits of the Cedar Creek project would be. So looking at a second quantification approach, in this case we're looking at the water quality benefits from a reduction in nutrient and sediment loading. And for this approach we use a different model. We use the nutrient tracking tool. And just like the Shadolator model, we incorporate a whole number of different current conditions and landscape conditions into those modeling scenarios. So we look at the soils that are present on the landscape. Again, we look at the topography, we look at the slope of the agricultural field, we look at precipitation patterns, how much rain, what the air temperature is, wind, relative humidity, all of those different pieces that drive things like evapotranspiration, how much water is used on a site. And then we also incorporate the land management characteristics as well. So what crops are being grown on the site? What tillage practices are happening? What sort of irrigation practices are being used by the landowner? And all of those are incorporated into a current modeling scenario to look at the agricultural runoff based on those current management conditions and characteristics of the landscape. And before we implemented the site, we had there was a buffer present, but it really didn't have the same level of filtering capacity or potential nutrient uptake as a healthy riparian forest would. So the only difference between the two modeling scenarios that we're looking at here is the removal of the invasive species and the planting of a forested riparian zone. And what we have with the difference between those two outputs is the water quality benefit from the Cedar Creek site, where we have a reduction in nitrogen, a reduction in phosphorus, and a reduction in sediment loads associated with the planting of a riparian buffer. And just to refine that a little bit more, when we're looking at the water quality benefits in the area of the adjacent land that we're actually modeling for the purposes of quantifying, we're not looking at that whole field. As you can see on the screen, there's a lot more field that is present and that's actively being managed than what will actually be draining through or flowing through that riparian zone. So what you have on the screen, those little blue arrows, represent water flow across the landscape. So we're looking at where the water is going once a rain droplet or a droplet of water from an irrigation event hits the ground. Where does it head when it flows across the landscape? And so we're only incorporating the areas of the agricultural field that flow through those riparian buffers for the purposes of estimating what sort of water quality benefit would be associated with this project. So you can see the green area that represents the drainage area of that agricultural field that then drains through the riparian buffer. So when we put all of the different results together, we can see the thermal benefits, the kilocalories per day reduction that's associated with the Cedar Creek Riparian project. We also have the water quality benefits from phosphorus, nitrogen, and sediment loads that are reduced through the filtering of agricultural runoff. And really the goal here is to identify as many of the environmental benefits associated with a riparian project as we can. We want to understand the full suite of benefits that come from the restoration work that we're doing so that we can account for those over time and understand the progress that we're really making towards improving conditions on the landscape. So I think we have a quick question that
yeah, Julia, could you address why specifically the south bank was planted with trees in the Cedar Creek example, and then address whether buffers on both banks might be beneficial or would produce sediment and nutrient reductions?
That's a great question. So for the question about why only the south bank, when we're looking at so the original goal of this project was improving improving riparian conditions with a focus on creating streamside shade. And in that case, at least with the movement of the sun across the landscape in our northern hemisphere, the south bank is able to shade the river more effectively than the north bank. So for the purposes of quantifying the thermal benefits associated with this project, the south bank is more effective at producing those thermal benefits. However, in terms of filtering capacity for agricultural runoff, the north bank, if planting a riparian zone on the north bank, would also produce benefits as well. What we do see in many of the cases of our project sites, though, is we tend to have a difference in land ownership that is oftentimes divided by the stream itself. So when working with an individual landowner, you're typically confined in many cases to one side of the stream or the other when you're developing a specific project. And by expanding it to the other bank brings in another landowner, additional agreements and other work. But where we can, we do try and capitalize on the proximity of projects to one another to try and increase the amount of environmental benefits that we can get from restoration projects. So North Bank project, if it's possible, or if there's an agreeable landowner on the other side, all of those add up and can continue to produce those benefits. All right. Another question.
Yeah, real quick before I move on to the next example, we have another question about, is it possible, or how do you define an ideal thermal load in terms of kilocalories?
An ideal thermal load. That's an interesting question. What we're looking at in many of our river systems is, in many cases, as much shade as possible is oftentimes the goal that we're looking at for many of the rivers, at least in the Pacific Northwest and particularly on our rainier side of Oregon. So that suggests down to a thermal load of 0, but that's usually not possible with riparian trees. So looking to reduce it as much as possible in order to protect water temperatures, but only where the vegetation really allows for that, because in some cases you have landscapes that are more arid, drier, where you really don't get tall trees that are able to shade the stream. And it kind of speaks to the importance of the location where you're putting your riparian revegetation project. Smaller streams can be shaded more easily compared to some of your larger streams. And so the effectiveness of reducing incoming solar radiation depends on the size of the water body that you're also looking at. But really, in terms of an ideal thermal load, there isn't a magic number that we're looking at. But what we're trying to do is understand the overall impact that an individual site can have and how that can stack up towards reducing incoming solar loads to a water body over time, especially as you start adding more projects. Well, great questions. Thank you. So I'm going to move on to another second example here. And the goal with this is really to just highlight the fact that while we can take multiple different actions on the landscape, there are lots of different kinds of restoration actions, but we still see many of the same water quality and habitat benefits associated with those different kinds of actions. So the Rock Creek example is a very different action. Instead of planting a riparian buffer, this is actually an agreement with an agricultural producer to leave the water that would have been removed from and withdrawn from the stream for the purposes of irrigation, and an agreement to leave that water in the stream to benefit fish during certain times of the year. So what we're seeing is very similar benefits associated with just a very different kind of restoration action. So to quickly highlight the quantification of this, when we're looking at an increase in in-stream flow, we can look at the improvement in water buffering capacity, so the thermal buffering capacity of the stream as a result of having more water in the stream during certain times of the year. And so before, we're looking at modeling a condition using In this instance, instead of the shadolator model, we're using the water temperature transaction tool, which is sometimes referred to as W3T. And the tool that we use allows us to model and capture a number of conditions of the project site, including the current in-stream flow, so how much water is actually flowing in the stream today, the water temperature, the characteristics of the channel itself, meteorological conditions on the landscape, so looking at the weather patterns, and then we can model a second scenario where instead of the previous amount of water that was in stream, we're looking at an additional amount of water that's in stream and calculating the change in water temperature as a result of leaving that water in the river. And what we see is that improvement in buffering capacity, which means it takes a lot more energy to warm that water temperature up. And if you've kept all of those other conditions the same, you're able to see a reduction in the daily maximum stream temperature. And that difference is the temperature benefit that we're seeing from water that is left in stream. So just here an example of the measuring and the irrigation withdrawal. So instead of withdrawing that river water from the river, we're leaving it in stream for the purposes of benefiting fish. And what we see are the temperature benefits of that. So in the case of Rock Creek, seeing a reduction in about 0.5 degree Celsius of the daily maximum temperature of Rock Creek itself as a result of leaving that water in the river. And in addition to the temperature benefits associated with that, using the nutrient tracking tool, we're able to also quantify the water quality benefits in terms of phosphorus, nitrogen, and sediment of the agricultural runoff that in this case is actually no longer occurring, since the water is no longer being withdrawn for that period of the growing season and it's no longer being applied to the landscape. It means that there's a level of runoff that's also no longer occurring, so that there's nutrient and sediment benefits to the river as a result of that change in in-stream flow. So with that, with a few examples under your belt, what I wanted to do was introduce you to a new way that we have been working to articulate and show the benefits of our restoration projects. So in the past, our Uplift Report has been really a very large table that we've been trying to present many of these benefits. And what I'd like to do is show you a new tool that we've developed that is a bit more interactive than, say, a very large table of results. And what is so exciting about this for me is that we're able to look at the benefits of our projects over time. So we can see how they're starting to stack up and see how they're making progress towards changing conditions on the landscape. So I'm just going to step you through a couple of examples that we have on here. So you can, if you haven't had a chance to play around with this, please do. You can get to the link on our website and feel free to check out the different components on here and play around. So what you have on your screen right now, the graph shows the thermal benefits in kilocalories per day of all of the restoration projects that we have implemented and been tracking and modeling since 2012. And the goal here is to really show how these projects continue to stack up and add up over time. And what you have, the light blue areas that are on here, each one of those individual slices represents an individual project that you can click on and you can see all of the details. And then the dark blue represents the cumulative benefits from the previous year. So what we're trying to do is continue to show that progress year after year. So I can come over here and drill down to that Cedar Creek project that you've seen before, and you can see the thermal benefits that we talked about here, and then you can also click on these other components to look at the sediment benefits. Now when you click on one of those additional icons, what it does is it shows you the benefits of that additional parameter across all of those previous years. So you can see how the Cedar Creek site, the red one over here, stacks up in comparison to the other projects that we've implemented over the years. You can take a look at nitrogen as well to see how it stacks up, and then phosphorus too, to see how Cedar Creek fits within the phosphorus load reductions that we're seeing from our different sites. And of course, we're describing the actions that we're taking. You can see the length of stream, so how many miles or feet of stream that are being protective, as well as the actions that are going on on the ground. How many trees and shrubs are we actually planting? And then being able to tie that back to the modeled benefits for water quality. So I'm also going to just show you the flow restoration. We were just talking about that with the Rock Creek example. And what's exciting to see here, like all of the other ones, is you can see how these things are changing over time. So if we're looking at the Upper John Day and we're looking at the voluntary flow deals that we have with landowners, in this case back in 2012 we were looking at 7 landowners benefiting 5 different streams with an uplift of 13 CFS, that's cubic feet per second. So that's what we have here on the y-axis, is the volume of water that is being restored or left in stream as a result of these projects. And we can see the progress over time. In 2013, we didn't have any additional deals with any landowners, but in 2014 that continued to increase. We're up to 17 CFS. And then in 2015, adding an additional 4 CFS to that to get us up to 21 CFS that is now being protected and left in stream in the Upper John Day Basin. So it's just exciting to be able to see this increase over time, to see how our projects are working together to improve those conditions on the landscape. And then of course we've been focused on presenting the numbers, but we also have developed the mapping component here as well, so that you can see where these projects are on the landscape. And you can also drill into the different specific locations to try, so you can see where these projects live, where they are on the ground, and then dig into the details. So here's the John Day again. You can see some of these individual projects, and your Rock Creek project is over here as well, where you can look at the nutrient and sediment benefits associated with that individual project. And you can filter back and forth to look at the different components. The other one that I wanted to highlight was stream function, that we hadn't had a chance to really drill into with any of these examples. But stream function is another component where we're looking at in-stream habitat characteristics that are benefited from our restoration projects. So instead of looking at some of those other parameters like phosphorus or nitrogen, when a project goes and implements, say, a large wood structure or reactivates a side channel or some other goal of increasing the amount of habitat in stream, we're looking at using a different set of units for the purposes of evaluating the progress of those projects. So in this case, we're looking at functional linear feet of stream. So that's the length of the stream channel, the length of the river that is providing a functional benefit to aquatic organisms, particularly with a focus for fish. And unlike many of our other uplift values, this one's actually going up. We're trying to increase the number of functional linear feet of stream that is present on the landscape, as opposed to when we're looking at agricultural runoff or solar loading, where we're trying to decrease the input of those parameters to a project site. So in this case, this is one of our Still Creek sites. We're looking at a little over 5,000 feet of side channel habitat that was restored, and implementing a number of large wood structures as well to see an increase in the functional linear feet of stream for that project. And again, like the others, we're seeing the improvements with that over time. So when we put in phase 2 of that project, an additional 732 functional linear feet of stream from that project. So we can start seeing again those upward trends as we continue to do this over time. And just to point out, back in 2012 we switched models, and we switched our quantification approach for in-stream habitat. And so we really don't have any 2012 values for our functional linear feet of stream, since we were using a different model in this case. And I think that that's probably a good side note for this as well, that these do change over time, and part of putting this online and presenting it in a different format gives us the ability to continue to refine our methods, continue to update our models, continue to make improvements to the way we are approaching our projects and approaching the way we quantify our work, in order to present them and evaluate them using the best available science at the time. We want to improve the way we go about our work. We want to make changes and use what's available and to make improvements. So what we plan on doing this year after year, continuing to add to this and continue to document the work that we're doing and adjust as necessary in order to do a better job of capturing the conditions on the landscape. So with that, I've spent a lot of time talking about modeling and talking about the parameters that we've used and the results that we're seeing. But what I wanted to also touch on here towards the end is how are we going to ensure project success? How do we ensure that these projects are continuing to produce the benefits that we've calculated? And how do we go about doing that? And so I guess that gets to my third M. You have your modeling, your measurement, and now we have our monitoring. And the goal with monitoring is to track the progress of a restoration site over time. In some cases, we have specific objectives that we want to meet. Say we have species diversity metrics that we want to be sure that our sites reach, and in some cases we just want to understand the progress of a site. We want to understand how it has changed over time, and by going to a site on a regular basis and performing quantitative or in some cases qualitative monitoring, we're able to collect the metrics that allow us to not only refine our models and refine our predictions over time, we also collect the information that allow us to make decisions about management actions at these sites. Are the invasive species starting to take over, and do we need to do something to address that? Or are things doing really well? And if so, why are they doing really well? Can we characterize the management or the stewardship actions that we took at the site that helped that? So with that, I wanted to give you an example of some qualitative monitoring that we do. And this is an example of photo point monitoring, where we go back to a site and from the same location, year after year, we document the progress of that site using photos. And so this is an example of one of our projects down in southern Oregon. And what you started with was the pre-project conditions, what it looked like before we put any plants, then planted. Then we're looking at 1 year of growth, 2 years of growth, 3 years of growth, and you're seeing how these trees have just taken off and they're just growing. They're just happy trees. And they're continuing to improve or continue to grow over time, and it gives us, I'm just going to go through it one more time, gives us the ability to track the progress of these sites, and we complement this photo point monitoring with vegetation monitoring that we do, where we're actually identifying the species that are at a site, looking at the density of species that are there, how many cottonwoods, how many alders, and also documenting the invasive species if they are there on the site, and any management actions that might need to be taken in order to improve conditions. So there's just there's a whole suite of monitoring that we do at these sites to try and ensure that they continue to thrive and are continuing to be on track to meet those future conditions that we're modeling, and gives us the opportunity to learn. It gives us the opportunity to refine and make improvements and improve the way we go about our work. So with that, I just wanted to thank you all first for being here with me today and for listening in on what we've been working on, and I'm happy to take any questions that we might have. Danielle?
Yeah, we have several questions to go through, Julia, and I think that last slide that you just discussed actually does address several questions that we had come in about how are we actually tracking or monitoring what these projects do. How do we validate what the models are telling us? So for the shade projects, I think you addressed that about the long-term monitoring, usually from 1 to 5 years until the trees are at a free-to-grow state, and then making sure the species diversity is present at those sites. Is there any other monitoring that you could discuss related to some of the other parameters, the sediment or nutrients or the water temperature?
Sure. We do a lot of monitoring for all of the different kinds of projects that we put in on the ground. And it really does vary with the type of project and some of the project objectives. But for example, with the flow agreements that we have, and if we're looking at those improvements in water temperature, we deploy not only flow gauges to monitor the volume of water that's present in the stream, but we also install temperature loggers as well. So we're recording water temperature of those different creeks under an assortment of different conditions to track that progress over time. We're also on some of the nutrient and sediment benefits. For the most part, a lot of the work that we do in terms of monitoring is looking at the conditions on the landscape and verifying those conditions are continuing to be consistent. The issue that we have with some of the water quality monitoring is that a lot of it can be very time and resource intensive in terms of being very expensive to implement on the ground. And so some of them, unfortunately, are just, they're not very feasible to really track some of the water quality benefits that we'd like to be able to see, just really dealing with some of the resource constraints that do exist. However, that's the benefit that we have of some of these models, is that we can use the best science that's available and the best models that do exist and inform them with measured values from the field. So we can inform them as best as we can with the different measured parameters that help us refine what we're actually seeing on the landscape, and then we can compare that to some of our in-stream monitoring that happens. So a lot of the comparison we do may not be at the field level, but actually aggregating benefits across the landscape and comparing those to in-stream water quality monitoring that may not necessarily be done by the Freshwater Trust, but may be a part of other organizations. For example, the USGS does a lot of great water quality monitoring that we benefit from, that we can compare our results to. So a lot of the validating that we do is looking at many of the different parameters that are used in the model and the models that we use. But we do also go out in the field and track the progress of habitat project sites as well. So we're looking at the increase in different at the increase in available habitat that's present in the specific habitat features. So pools, riffles, counting the number of large wood, tracking the substrate within the stream, and how that changes over time. So there's a lot more modeling detail, or excuse me, monitoring detail there. So I've got another question here. I think that it pertains to the models that we are talking about today, and it was, can we repeat the models that we use? So the first one, for looking at reductions in solar loading, we use the Shadolator module of the heat source model, and it is a model that is maintained by Oregon Department of Environmental Quality to model in-stream water temperatures and riparian conditions. The other model that we're looking at for nutrient and sediment benefits, that's called the Nutrient Tracking Tool, sometimes called NTT, and that's available. It's a web tool. You can find it online, and you can run a number of different operation scenarios to model the land management actions. Then the third one is the Water Temperature Transaction Tool, sometimes also known as W3T, and that one is for modeling in-stream water temperatures, and we use it for the purpose of modeling the difference in water temperature as a result of a change in flow. So looking at a couple of these other questions that we have here. One of the questions is, do the projects that you've discussed tie into basin-wide restoration efforts and the work of other groups in the basin? Which is a great question, and part of the reason why we've been trying to work to aggregate some of the results of our projects. In some cases, I will say, of course, it depends, and it depends on the basin that we're talking about. In the Rogue River Basin, we've been working there for a few years now on riparian revegetation projects primarily, but then also working with some additional projects that look at the installation of large wood structures as well as riparian revegetation. And the goal of these projects is really to tie in with improving those riparian conditions and other in-stream conditions, and trying to document those within the context of some of the broader efforts that are happening. Expressing all of those with the same units, I think that piece can be a little tricky, but the actions that we're taking are typically designed to fit into a larger basin restoration effort. Some basins have specific targets that have been set for certain things. For example, a lot of our salmon river work that we do, we have specific habitat targets that we're working towards with a number of different other partners, and those are quite clearly laid out in terms of the amount of in-stream habitat that we want to see. But in other basins, the targets are a little less clear and a little less defined. So I've got another question here. How are these models and the quantification methods used by regulators to make decisions regarding use? So I think there's a number of different pieces that can fit within this particular question. Many of the models that we use have been directly approved by regulators, particularly here in Oregon, to be used for the purposes either in some of the work that they do. So for example, the heat source model, which includes the shadolator module, is a water temperature model that is used by the Oregon Department of Environmental Quality to develop temperature total maximum daily loads for rivers in Oregon, TMDLs. And the methods that we're using here to evaluate the benefits of riparian shade follow many of the same methods that are incorporated by the Oregon DEQ regulators to evaluate the impact that a lack of riparian shade has on water temperature, or the benefits or the change that's necessary to improve conditions. So in that case, the method has been approved for use in the water quality trading world here in Oregon to use riparian revegetation projects as a means to offset the impacts that a discharger might have in Oregon. And so we use the shadolator module to quantify that and use that for the purpose of tracking those benefits over time. Then there's other, I think many models feature into decision making that's used by regulators to understand what sort of actions are needed on the landscape, and also what the size of the impact of current conditions actually is for many of our rivers. And so modeling plays an important part of evaluating what's happening on the landscape, but then also what sort of benefits are necessary for the purpose of improving conditions. The next question I have here is, does the tracking and quantifying of environmental uplift attract the interest of funders? I think that's an interesting question. What we have found with changing our approach and working to track and quantify the environmental benefits of our restoration actions is it gives us the ability to speak to the benefits of restoration in a way that hasn't really been expressed very well before. And where I think the interest has come from for funders in some cases has been the fact that they are potentially switching their approach from paying for actions to paying for outcomes. And I think that's really quite a fundamental shift for some folks, and I think it's very interesting to have that shift as well, so that instead of just paying for the number of trees that are planted, you know that you're actually paying for an outcome on the landscape, an actual environmental improvement to streams or rivers as a result of, say, planting a riparian buffer. And that has certainly increased the interest of funders, and it's really been part of the reason why water quality trading and other restoration for regulatory compliance has become as interesting and has as much potential as it does today, is because we can tie those two together now. We're able to look at how an action might, once it's implemented, benefit a system and work towards addressing those environmental impacts that are present for our rivers and streams today. So let's see, another question here. What is the timeline, for achieving uplift? And with the follow-up question of, do modeled benefits sometimes produce results more quickly or slowly than modeled? I think the timeline question is a great one. When we're looking at implementing a restoration project, I would say that it definitely depends on the action that you're taking. If you're thinking about something like leaving water in stream, no longer withdrawing it, the benefit of that is immediate. As soon as the water is no longer being diverted, it is present in the water body and it acts as habitat for fish and it acts as a buffering capacity for increases in temperature. That benefit, that uplift, is immediate. And if that water is no longer left in stream and diverted, that benefit is gone. On the other hand, I think the other side of the other side of that whole spectrum is riparian revegetation. Those trees, if anyone's planted a tree and watched it before, knows that they take time to grow. It takes many, many years before a tree reaches its mature height. What we do have, though, is as those trees continue to grow, and what you saw hopefully on those photo point slides from just before, is that while when they're immediately planted, the shade from a little tiny tree it's not much, but over time, and honestly quite quickly, especially when those sites are stewarded well and maintained well, that shade really does start to accrue as soon as those trees start to take off. And the immediate benefit that you have is pretty quick. You have that within a few years. And you also have all of the other ancillary benefits as well. You start having additional habitat, the filtering capacity starts developing as well. And the bank stabilization components associated with a vegetated stream bank, reduces stream bank erosion, and all of those things are far more immediate than, say, the long-term shade that you would necessarily see. So yes, the modeled benefits do produce, sometimes they are fast, sometimes they are slow, and it really is dependent on the type of action that's taken.
Okay, thanks, Julia. We're getting close to the end of our time, so I think we have time for possibly 2 more questions before we wrap up. And I'd like to thank everyone for all the questions that they've sent in. There have been some really good probing and wanting to dive into the details of what we're talking about here. So we'll turn it back over to you.
So the next question that I have here is, how can these benefits be traded by dischargers in a regulatory context? And since I only have a few minutes here, I am confident that I will not be able to address all of the components of this question, but I think we have a lot of good information on our website. If you want to dig deeper, feel free to contact us afterwards. But the general idea of looking, and this question is getting towards the idea of water quality trading, is that when you have a discharger, so you have a permit holder who is discharging to a water body, in some cases what you have is you have effluent, you have discharge that is going into the water body that is typically clean but may be slightly over the water quality standards that apply for oftentimes for a short period of the year. And the technology solution for this can often be incredibly expensive to address this very, very small amount of pollution that is coming from a discharger. And what we're seeing in many parts of, particularly in Oregon, but also in the United States in general, is that oftentimes addressing these environmental impacts that we're seeing in our rivers and streams, the mechanisms of addressing them through regulating point sources does a great job of reducing and limiting a lot of the impacts that come from these potential sources of pollution. However, many of the issues that we're seeing today, after many decades of successful implementation of the Clean Water Act, we're seeing that a lot of those ecological conditions, so riparian conditions, so streamside trees, for example, they've been removed through land management actions over the years, and they represent one of the key components of shading and improving thermal conditions in a river, but there's no real mechanism to necessarily get those projects happening on the ground except through typically philanthropic means or other grant funding programs. So by being able to quantify the environmental benefits of a riparian restoration project, we can translate those benefits into the same units that a discharger is regulated on. And by doing that, we have the same language, if you will, the same currency that can be evaluated in terms of the impact from a discharger and the benefit that happens on the landscape what we're really looking at is green infrastructure and using natural infrastructure to improve water quality conditions in stream instead of using gray infrastructure, your concrete and pipes, to address a very small amount of pollution load. So there's a lot more details that to get into there than I'm able to cover right now, but I'd say that the key piece that is that translation between the two, using the same units and expressing the benefits of a restoration project using the same units that are used to regulate a point source discharger. So the last question I think we're going to have for today is, what portion of time is spent on modeling and monitoring versus implementing restoration actions? And I think this is kind of looking at the breakdown of the process and how much time is spent where, and then the funds that are spent in different places. The bulk of our time and efforts are focused on the implementation and monitoring. The modeling piece is honestly a relatively small component of the work that we're doing, and which is when we're looking at while it does take a fair bit of time, I'm not going to lie, the bulk of our staff time and the bulk of our resources are spent on the implementation of a project, and then that long-term, not just the monitoring, but also the maintenance and stewardship of that project over time. So addressing conditions, taking corrective action as needed, invasive species treatment, for example. And so that's where I'd say the time breakdown, the bulk really is on that implementation and the monitoring, and then the maintenance and stewardship. The modeling is a much smaller time component and a much smaller resource component.
All right, thank you, Julia. And thanks to everyone who attended today and asked some great questions. Right now, at the end of the hour, this is going to conclude our webinar. And we are available to follow up via email if you have additional questions or seek additional detail about what we've discussed today. Thanks everyone for joining us.